topologies, ISO OSI 7 layer model. This slide introduces the OSI model, which stands for Open System Interconnection. The key message here is that whenever two devices communicate over a network, there's a structured process happening behind the scenes. And the OSI model is the framework that describes the process by breaking it down into 7 distinct layers. Starting from bottom layer is the physical layer, the most basic level, dealing with raw electrical signals, cables and hardware. Layer 2, data link, takes those raw signals and organizes them into meaningful frames, handling local device to device delivery using MAC addresses. Layer 3 network is where routing happens, where IP addresses come in and data finds its path across different networks. Layer 4 transport is about reliability, making sure data arrives fully and in the correct order. The top 3 layers shift from hardware concerns to software. Layer 5 section manages the opening and closing of communication sections. Layer 3 presentation handling translation, encryption and compression. And layer 3 application is what the end user actually interacts with: browsers, email clients and apps. The diagram on the right reinforces the key distinct layers. 5 to 7 are the upper software layers closer to user, while layers 1 to 4 are the lower hardware layers dealing with the physical movement and routing of data. Next, OSI layers for upper layers. Now, let's zoom on top 3 layers, the one that interact mostly directly with users and application. Layer 7. The application layer is the point of contact between the network and the software we used every day. It's not the application itself, but the protocols that allow applications to communicate. When you open a browser and request a web page, the HTTP at work and HTTP lives at layer 7. Other protocols here include FTP for file transfer, SMTP for email, and DNS for translating domain names into IP addresses. Moving down to layer 6, the presentation layer. This is where data gets translated into format the receiving system can understand. Think of it as a universal translator. It also handles encryption, so when you see HTTPS in your browser, SSL and TLS encryption is happening at this layer. Layer 5, the section layer, is responsible for establishing, maintaining and terminating communication sections between two devices. It also handles recovery, so if a section is interrupted, it can pick up from where it left off rather than starting over. A practical example is managing a login section on a web application. Next, OSI layers in lower layers. The lower 4 layers are where data physically moves from one device to another, and each layer plays a very specific role in making that happen reliably. Layer 4, the transport layer, is the responsible for end-to-end delivery. It breaks data into segments, manages flow control and handles error recovery. The two key protocols here are TCP, which is reliable and ensure every packet arrives correctly, and UDP, which is faster but does not guarantee delivery. Port numbers also live here. They tell the receiving device which application the data belongs to. Layer 3, network layer handles logical addressing and routing. This is where IP addresses comes in. Protocols like IP, ICMP, ARP and routing protocols like OSPF and BGP determine the best path for your data to travel across the internet. Layer 2, the data link layer, handles node-to-node communication, meaning device to device on the same logical network. It uses MAC addresses and organizes data into frames. It splits into two sublayers. LLC handles error checking and flow control, while MAC controls how devices access the shared medium. Layer 1, the physical layer, is the most fundamental. It transmits raw bit adds electrical, optical or radio signals over a physical medium. Everything from the voltage on a hopper wire to the type of connector used in defined at this layer. Next, TCP or IP model. Now we move into the theoretical OSI model to the practical TCP/IP model, the framework that actually powers the internet as we know it today. Where OSI has 7 layers, TCP/IP consolidates them into 4. The application layer in TCP/IP combines OSI sections, presentation and application layers. The transport layer maps directly across. The internet layer corresponds to OSI network layer, and the network access layer at the bottom combines OSI data link and physical layers into one. The important point here is the OSI is the reference model. It helps us understand and discuss network concepts. TCP/IP is the actual implementation. It's what your devices are using right now to send and receive data. Both models are useful. OSI for understanding, TCP/IP for practice. Layer protocols. This slide focuses on one of the most important choices in networking, TCP versus UDP. Both operate at the transport layer, but they serve very different purposes. TCP, the Transmission Control Protocol, is all about reliability. It establishes a connection using a three-way handshake before any data is sent, guarantee that packets arrive in the correct order, and retransmit anything that gets lost along the way. It also manages flow and congestion control. The trade-off is overhead. All that checking takes time and bandwidth. TCP is ideal where accuracy matters. Web browsing, email, file transfers, and SSH all use TCP. UDP, the user diagram protocol, takes the opposite approach. It sends data without establishing a connection first, does not check for the lost packets, and does not wait for an acknowledgement. This makes it extremely fast with very low latency. The trade-off is that some data may be lost for applications like video streaming, online gaming, DNS lookups, and VoIP calls. Losing occasional packet is acceptable, but delays are not. UDP is the right choice there. Next, network layer protocols. The network layer relies on several protocols, each solving different pieces of routing and addressing puzzle. IP, the Internet Protocol, is the core of the end-to-end Internet. It handles addressing IP4 with 32-bit address and IP6 with 128-bit address to accommodate the billions of devices we have today. IP is connectionless and operates on a best effort basics, meaning it tries to deliver packet but does not guarantee it. That's TCP's job. ICMP, the Internet Control Message Protocol, is used for diagnostic and error reporting rather than the data transfer. When you run a ping command or use a trace route, you are using ICMP to test network connectivity and the trace path packet state. ARP, the Address Resolution Protocol, bridges the gap between layer 3 and layer 2. When a device knows IP address but needs the corresponding MAC address to actually deliver data on a local network, it sends out an ARP broadcast to find it. OSPF, Open Shortest Path First, is used to inside large enterprise network to calculate the most efficient internal path. PGP is used between internet service providers and autonomous system. It's often called the protocol of the internet because it's how different networks around the world communicate and share routing information. Next, data link layer protocols. The data link layer is split into two sublayers, which is worth noting. The LLC or logical link control sublayer handles error checking, flow control, and protocol identification. The MAC, media access control, deals with hardware addressing and controlling how devices access the physical medium. Ethernet, defined IEEE 802.3, is the most common wired LAN technology. It uses CSMA or CD, carrier sense multiple access with collision detection, to manage when devices can transmit. Modern Ethernet supports speeds from 10 megabits all the way up to 100 megabits per second. Wi-Fi, defined by IEEE 802.11, is the wireless equivalent. Instead of collision detection, it uses CSMA or CA, collision avoidance, because detecting collision violence is most difficult. The standards have evolved from Ethernet 2.11a and B through Ethernet 2.1111ax, which is Wi-Fi 6 operating on both 2.4 GHz and 5 GHz bands. PPP, point-to-point protocol, is used for direct connections between two modes, such as dial-up and DSL links. It supports authentication, encryption, and compression. SDLC is the more foundational bit-oriented protocol used in WAN environments, and it actually forms the basics for PPP and several other protocols. Next, data versus signal. Before we discuss transmission in detail, it is important to distinguish between two terms that are often used interchangeably but mean very different things: data and signal. Data is the abstract information we want to communicate: text, numbers, images, audios, or video. It is conceptual. When you type a word hello, they exist as a sequence of bits, 8-bit ASCII values for each character. Data lives at the high layer of the network model. A signal, on the other hand, is a physical representation of data. It travels over the medium. It concrete and measurable. Electrical voltage changes on the copper wire, light pulses through fiber optic cable, or radio waves through the air. Signals exist at the physical layer. A key takeaway is before data can travel across a network, it must be converted into a signal. And when it arrives at the destination, that signals must be converted back into data. Everything at the physical layer is about managing the conversion and transmission accurately. Next, types of signal: analog versus digital. There are two fundamental types of signals, analog and digital. An analog signal is a continuous smooth waveform that can take on an infinite range of values, sound waves, AM and FM radio. And traditional telephone signals are all analog. The challenge with analog is that highly susceptible to noise. An interface along the transmission path can distort the signal and degrade the data. Digital signals uses only two discrete values, high and low, or 1 and 0. All modern computer communications uses digital signals. The key advantage is noise immunity, even if a digital signal picks up some interface. It can be regenerated perfectly at repeaters along the route because you only need to distinguish between two states. The comparison table on this slide highlights the core difference in terms of bandwidth. Digital signal actually require more bandwidth than analog. But the benefit of being able to regenerate and error correct them makes digital the overwhelming choice for modern networks. Next, signal properties and key terms. Understanding how signals are characterized is essential for understanding network performance. This slide covers 6 key properties. Amplitude is the strength and height of the signal measured in volts. A higher amplitude means stronger signal that can travel further before degrading. Frequency is how many wave cycles occur per second, measured in hertz. Higher frequency means more data can be transmitted per second, but the signal does not travel as far. Phase refers the position of waveform related to reference point, measured in degrees. It's used in advanced modulation technique like QAM to pack more data into each cycle. Wavelength is a physical distance that a wave travels in one complete cycle. It's inversely related to frequency. Higher frequency means shorter wavelength. Bandwidth, it's the analog sense. It's the range of frequency a signal occupies. In digital terms, it's the maximum data transfer rate. Wider bandwidth means greater capacity for data. Finally, the noise refers to any unwanted interference and that distorts the signal. The signal to noise ratio is the standard measure of signal quality. One of the biggest advantage of digital signals is that can self-correct at repeaters, making them far more resistant to noise than analog signals. These are the references. Thank you.